My name is Vladimir Jacome. My subject, Mendelian Randomization. I'm a student of eye clot and cardiovascular disease. Definition. Mendelian randomization is a method that uses measure variation in genes what now function to examine the causal effect that a modifiable risk factor as on disease in observational studies. Mendelian randomization uses genetic variants to determine whether an observational association between a risk factor and an outcome as consistent with a causal effect.
Epidemiologists are interested in understanding factors related to health and disease. Do smokers tend to die younger than non-smokers? It certainly looks that way. But disentangling cause and effect can be difficult. Smokers are different on average from non-smokers. They're more likely to drink heavily and have less healthy diets. But even if we measure these confounding factors, we may not measure them perfectly, or there may be others that we haven't measured. Also, as people become ill, they may cut down or give up smoking, which could wrongly suggest that reduced smoking leads to worse health. We could randomly assign 50,000 people to smoke and 50,000 people to not smoke and follow them up to monitor their health. This removes the possibility that any other factor could be responsible for any differences we see in their long-term health. But this is neither ethical nor practical. Fortunately, we have all been recruited into an experiment without knowing it at the point at which we were conceived. Our genes, which are passed on randomly from generation to generation, influence how much we eat, sleep, drink, smoke and more. These genetic influences are not affected by anything else you may or may not choose to do in your life. They're not related to confounding factors. We can use this knowledge to learn about cause and effect, grouping people according to their genetic code. This method is called Mendelian Randomization. For example, smokers who carry one version of a gene called CHRNA5 tend to smoke less heavily than those who carry a different version. When we group people according to which version of this gene they have, we find that the people with the version of the gene associated with heavier smoking do indeed die younger. But is the gene influencing how long we live in some other way? We don't think so. When we look at the same gene in non-smokers, there's no effect on life expectancy, so the effect must be driven by smoking. Using this method, we can show that smoking causes lung cancer, heart and respiratory disease, and many other diseases, but does not seem to influence depression or anxiety. Mendelian randomization has already begun to tell us about factors that influence our risk of disease. Now we're using the same approach in other ways to look at several risk factors together and to look at what influences disease progression, which may help us to develop new treatments.
For example, two examples. Pros. Identify modifiable cause of diseases concerning public health. Uses common genetic polymorphism with will now effect of exposure pattern. Association can be found with logic that confer benefits of protection against a possible pathological trait. Cons. They require a lot of time. They can be impractical to carry out. Another limitation is the statistical power. Mendelian randomization depends on previous genetic association studies.
There's another type of study that I love to cite and talk about because it's a way, as you had mentioned previously, randomized controlled trials are very, very expensive to do. They're very difficult. They take a long time. It's a challenge. So another way of measuring more of a causative role of maybe, of certain factors, and particularly in this case, lifestyle factors, or something that, I call vitamin D a lifestyle because you're making it, from the sun. They're called Mendelian randomization studies. And essentially what they do is they measure, so everyone has, different variations in the sequence of DNA in their genes. And these variations often are just a change in one DNA nucleotide, which is called a single nucleotide polymorphism, or a SNP for short, as you know. But for people listening and watching, there are many different variations in genes that convert, for example, 25-hydroxyvitamin D, the major circulating metabolite of vitamin D, into 1,25-hydroxyvitamin D, which is the active steroid hormone. And these changes in just one nucleotide of DNA in these genes are associated with lower circulating levels of 25-hydroxyvitamin D because, it's just that, different genes are doing different things, and sometimes genes get less active and sometimes they're more active based on this, sequence change. So it's well known that these certain SNPs are associated with lower circulating 25-hydroxyvitamin D levels. And so there have been meta-analyses looking at people that have the SNP, didn't measure vitamin D levels at all. It's already known they have lower circulating levels. So you can't say, you're just measuring their low vitamin D, that's biomarking another health status. This is just genetics. We're just looking at a gene that's known to cause that. And these people have a much higher mortality from respiratory tract infections. They have a higher all-cause mortality. They have a higher cancer mortality. Cardiovascular-related mortality is unchanged. But respiratory tract infections are much higher. And so that Mendelian randomization study, I love to cite that because it really is establishing causation, because it's not, you're not just measuring vitamin D levels and then saying, well, maybe they're low in vitamin D because they don't go out and exercise, or maybe they're low in vitamin D because they're, obese and the, vitamin D is less bioavailable, which it is in obese individuals, as you mentioned. So the Mendelian randomization studies are another sort of, in addition to the randomized controlled trials, I think another piece of evidence that hints towards possible causation of vitamin D being important for preventing respiratory tract mortality as well.
This is cardiovascular. Application in medicine. Akeley and genetic score hit similar association with multiple different composite cardiovascular outcome, as well what the individual component of the composition comes, inclusive the from coronary heart disease. Used applied in Ecuador. I5 Ecuadorians between the age of 69 have high blood pressure, all with approximate here 45 that they are diseased.
Heart disease is the leading cause of death in the world. Approximately 1 in 2 men and 1 in 3 women develop heart disease during their lifetime. In an effort to learn more about this disease, scientists noticed that people who spend more time in education are less likely to develop heart disease. This finding is interesting. However, what so far has been a mystery is whether this relationship is due to cause and effect. For example, other factors can give the impression of a cause and effect relationship, when in fact, these other factors are causing both heart disease and education. One way to check if more education prevents heart disease is to do a randomized controlled trial. For example, take a group of young individuals, some with high physical activity, some with low, some with good diets, some with bad. Randomly shuffle them into two groups. Give one half more education and give the other half less education. Then wait about 40 years to see which of the two groups develops more heart disease. Such a trial would give us the most reliable evidence on whether more time in education is protective of heart disease. However, this trial is virtually impossible to do because of the long wait time. So researchers of the current study did the next best thing. They mimicked a trial by looking at randomization that occurs in nature. In every human, all genetic material is randomly allocated from their parents, including 162 DNA markers linked to education. Some people randomly receive more of these 162 DNA markers, while others receive fewer. Just like in a randomized controlled trial, the beauty of this natural trial is that the allocation of educational DNA markers is not linked to any other factors, such as diet or physical activity. Researchers then asked the question, do people with more of these 162 DNA markers, and therefore slightly more education, develop less heart disease later in life? The answer is yes. The group with more education developed about 30% less heart disease. This finding suggests that longer education prevents the future development of heart disease. This means that doctors, public health experts, politicians, and civil society groups who advocate for more education may also be doing a big favor for the health of our hearts.
Conclusion. In conclusion, we can here highlight that studies are present as an essential experimental approach with to handle the etiological foundation of numerous cardiovascular diseases. Thank you.